discussion is a project that Josh and Greg came up with on their own, and it was last spring, and have worked on it since then. And so it's dealing with filters and guitars and fun stuff. So I'll let these guys talk about it.
Thank you, Dr. Music. For our project, we designed a filter effect for the electric guitar. Before we begin, we would like to recognize certain groups and individuals for their help with this project. Ms. Donna Moore, Dr. Dearson, our senior advisor, Dr. Cuban, Professor Sprouse, Dr. Kissel, as well as our families. For our senior design project, we designed a device to be used with the electric guitar. The function of this device is to remove parts of the guitar signal, such that when the guitarist plays a wrong note, the system will remove it. We will accomplish this using filters. A filter emphasizes or removes specific frequencies in a signal. This slide outlines the topics covered in our presentation. First, we conducted research to identify the parts of the musical scale that we need to remove from the guitar spectrum. Then we use that information to design a filter used to make a prototype of the system. Next, we use concepts from signal processing to simulate our filter and outline the system's process. After that, we chose a suitable DSP, which is a specialized microprocessor used for real-time digital signal processing, as well as any other additional hardware needed to implement our system. Then we created our filtering system in the DSP software, and we identified problems with our system and developed solutions accordingly. Last, we do a cost evaluation associated with this device and summarize our conclusions. Following that will be a short question and answer session. This figure shows the layouts of the notes on a standard fretboard of an electric guitar. On a standard guitar, 4 octaves are available, with the lowest highlighted blue going to red, yellow, and green. A note in 1 octave has a frequency that is half the note in 1 octave higher, such as E2, shown here, has a frequency of 82.4 hertz, as you will now hear. A note in 1 octave up has double that frequency, 164 hertz. In this way, the frequency doubles with each octave. The most common form of the musical scale used today is known as the 12-note equal temperament tuning. In 12-tet, a scale is divided exponentially into 12 intervals, or notes, where each note is the 12th root of 2 multiplied by the frequency of the previous note. In this way, the scale repeats at the 13th note. In contrast, the major scale is a subset of notes in the 12-tet scale, only 7 notes. The 7 notes are shown in green, starting with the bass note in red. The key is named after the bass note. Shown here is the key of E. As the key is changed, the relationship between these 7 notes remains constant. Notice that as you change from the key of E to the key of F, this pattern remains the same. And again for the key of F sharp. From this pattern, we are able to determine the frequencies contained within any key, given only the base frequency of that key. This will be important to allow us to calculate the mathematical model of our system. When a note is played on a guitar, many frequencies are created. We used a spectrum analyzer to plot the frequencies generated by striking the low E string. The first peak shows the base frequency of this open E string, with 82.4 hertz. The other peaks indicate the presence of 10 important harmonics, which are each multiples of that base frequency. These harmonics must be considered because they define the quality of the guitar's sound. The magnitude here is shown with a logarithmic scale known as decibels, where 0 decibels is associated with no attenuation or reduction in volume. On average, we notice 40 decibels of attenuation between the peaks and valleys of this plot. And we use this to help design our filter specifications. To summarize, in a given key there are 7 notes in 4 octaves, each with 10 harmonics. All total gives us 280 frequencies in any given key. For our project, we will design a filter for 1 frequency to prove that this concept is possible. Afterwards, the process may be repeated to create and implement filters for all 280 frequencies.
Our ideal filter specifications were chosen based on many considerations. As described earlier, the next and previous frequencies of a full scale are determined by the 12-TET interval. For a 330 Hz filter, the next and previous frequencies are 350 Hz and 311 Hz. These will be called the stop bands, which need to be attenuated. Frequencies not between the stop bands are not wanted, and their magnitudes must be reduced. For this design, these frequencies were held to a magnitude of -40 decibels, or about 1% of their original magnitudes. Other frequencies' magnitudes will increase as they approach the central frequency of 330 Hz. The white line shown shows the desired shape of the frequency response of our filter. MATLAB was used to derive our filter transfer function because of its filter development tools and functionality. The filter types tested in our design include the Butterworth filter, Chebyshev 1 filter, Chebyshev 2 filter, and the elliptic filter. The Butterworth produced a 12-order filter for the specifications given. Both Chebyshev filters were tested next and produced filters of the 8th order. Last, the elliptic filter produced a 6-order filter. As a test, a central frequency of 330 Hz was input into the MATLAB program, and the frequency response was plotted. As shown in the figure, the filter met the specifications. The elliptic filter was chosen in our design because it had the lowest order, which means less memory would be required to implement it. Also, the elliptic filter is known for having the fastest attenuation and gain of all the filters that were tested. Now that the filter had been designed, it had to be tested. This was done using a 330 Hz sine wave input. As the figure shows, the filtered signal's response rose to approximately the same amplitude as the input wave, just as expected. To be sure this result was stable, the filter was tested for a couple of seconds, and as shown, it is stable. To be thorough, a 311 Hz sine wave was input into the 330 Hz filter. As the figure shows, the filtered signal is a sine wave with an amplitude of 10 to the negative third, or about 0.1% of the original amplitude. Again, this result was stable. After these tests and several others, we concluded that our filter was functioning as expected. In an analog filtering system, the whole process can be completed using discrete components such as resistors, capacitors, and operational amplifiers. The benefit to an all-analog approach is no loss in signal quality, which is usually associated by the digital conversion process. However, a filtering system of this order would require complex circuitry. The more components that are used, the more power is consumed. Also, an analog system usually requires more space than the digital counterpart. Thanks to progresses in modern technology, digital systems now surpass analog thanks to the ease of implementation, versatility, and cost effectiveness. However, with any digital system, some minor loss of signal quality is expected. Another common problem with both systems is their single point of failure. This means that if one component fails, the whole system fails. However, debugging software makes the digital application much easier to troubleshoot, where a failure in an analog system is more difficult to identify.